Our next speaker is Graeme Smith from the Institute for Quantum Computing in Waterloo, who will break the trend and tell us something without using a computer.
You pass that over. I have the mic here. Sorry.
And are you okay with this talk being recorded?
Sure. Okay. Thank you. I'm Graeme Smith from University of Waterloo. I work on sort of information theory questions mostly. I'm grateful to be here to listen to the talks and tell you a little bit about what I've been doing lately. So I want to tell you about some joint work I've done with Nick Leroquente, and also, well, okay, let me just write the title first. It's about information fragility. Fragility or robustness under quantum channels. And you can find, it's with Nick Leroquente. Paper archive 2312, 17450, appeared on the 29th of January. I said it would happen that year, and it did. And this also talk is going to include some upcoming work with Peishu Wu, who's in Waterloo, and that's going to show up next week. Second talk so far that promises that. Sorry. Okay, so what are we interested in? Well, the general problem that I want to talk to you about is you have some quantum state. It's bipartite. It's got an Alice and a Bob, and there's going to be some noise process that acts on the B system, and it's going to have some strength P. And the question is basically, how much does that? I'm just going to take 1 second to fix my mic because it's doing something weird. The question that we're looking at is how much is the correlation degraded? If there's some correlations between A and B here, how much does this noise process degrade the correlations that start out you start out with? And the intuition that I want to explore is that small noise is going to imply a small change in correlation. And what we're going to see is that in some senses that can be true, and depending on, and in some cases it's not. And what it's going to depend on is what do we mean by a small change, and how are we measuring the correlations between the two parties. Now, this is a kind of, I think, a very interesting general question. In the background is a set of questions about information theoretic quantities. And I'll tell you a little bit about the applications of our findings towards the end. So let me just make a little outline here. First, I want to tell you about which correlation measures and noise we're going to look at. Then I want to talk to you about a particular notion of having a small change, which we call multiplicative stability. It's particularly stability. It's particularly relevant, or not. It's particularly relevant for situations where we have very small correlations between A and B, and we have a very small amount of noise. And then I want to, having shown you some multiplicative stability results and also some cases where it doesn't hold, I want to show you some applications to basically information theory. And specifically to private classical communication. And quantum capacity. So what's your favorite correlation measure? Think of it. You should get it in mind. Huh? Mutual information. Wow. It's a good one. I'll put it down. Yeah, and it's one that we're going to look at. Mutual information. Can you see this part here that's in the shadow? Okay. Mutual information is, sorry, I almost said to you, well, the mutual information is just the mutual information between A and B. But I understand that that's not actually going to help that much. Before I tell you that, actually, I should tell you the entropy, right? Entropy is equal to minus trace rho log rho. And then sometimes if I have a system A, instead of writing down entropy of the density matrix, I might just write down entropy of A. The mutual information, it's given by, well, this is the symbol for it, and it's just the entropy of the individual term, the individual systems, minus the joint entropy. So it tells you how much, well, it measures kind of how much correlation there is between them, the two systems. Another quantity that you saw in the previous talk is the relative entropy. It's closely related. It's given by, it tells you sort of, basically it's a distance-like thing that tells you how close two states are, and it's given by trace of rho, log rho minus log sigma. One of my favorites, if I had to say a favorite one, it would probably be the coherent information. And this has a special symbol. Coherent information from A to B, evaluated on some state rho AB, is equal to the entropy of B minus the joint entropy. And it's closely related to how much entanglement you can extract from rho AB. Okay, we're back. Actually, you can express it in a slightly different way if you purify rho AB to some state, some pure state on AB and an environment E. Then you can also write this mutual information as half the, or this coherent information is half the mutual information between A and B minus the mutual information between A and E. So it tells you something about how much stuff is there that's only correlation between A and B. And the last correlation measure I want to tell you is, it's called the advantage. I'll tell you about that in a second. Let me tell you about the channels we're going to look at first. Well, we're looking at a couple of channels. The depolarizing channel that takes some state rho, and with probability 1 minus T, P leaves it alone. Probability P replaces it with a maximally mixed state. This is on a qubit. And the amplitude damping channel, which basically models if you have a photon that might get absorbed by the medium it's traveling through. You can write it down like this, where the cross operators are this and this. And actually, both of these, you can get a Lindblad generator and generate them sort of, there's a, as a function, you can generate the, well, they're Markovian, and they form a semi-group just like the ones that we saw in the previous talk. And actually that's going to be of interest to us. What we're going to want to look at is how do these two channels degrade these kinds of correlation measures. And yeah, so the first thing I should say, I wanted to give you one more correlation measure, if we don't mind. It's called the advantage, the quantum advantage. And this tells us about the correlations that exist between some system V and the output of a channel. So it's a function of both a state and a channel. And it's just given by the mutual information between V and the output of the channel minus the mutual information between V and E, the purifying system that, that purifies the channel. What I mean by that is any channel I can write as an isometry with an output V and a traced out environment E. And this advantage just says how much more mutual information does B have about V than E does. It's almost exactly the coherent information, but with the additional feature that coherent information really is evaluated only on a pure state that purifies A, whereas this is evaluated on an arbitrary state. So the first thing I can say is, I want the outline to stay there, and I want this to stay there, and it's not a computer, so we're in trouble. I think we'll manage. I know what to do. So first off, the entropy itself is continuous. So let's just look at an example question. How does the mutual information between A and B on some state rho AB compare to the mutual information between A and B on rho AB acted on by a depolarizing channel? Well, the entropy itself is continuous. And what that means is if I have two states rho and sigma that are close, then their entropies are close too. Specifically, it's given by this Fannis inequality, where this is the binary entropy function that goes to 0 when epsilon goes to 0. So this tells us we can use this to show all of these correlation measures, and indeed that one too. If you take two states that are close together within epsilon, then there's a function of epsilon that goes to 0 as epsilon goes to 0, and depends on some of these binary entropy functions and log the dimension, that tells you they're going to have roughly equal mutual information, roughly equal divergences, roughly equal coherent informations, in the sense that if I take the difference and look at the size of the difference, it's going to be something like, the difference is going to be something like, some constant times this, plus some epsilon times some other constant. So that's great when you have a lot of correlations. But if you're in a situation where actually the amount of correlation that you have is comparable to the distance between the states, right, to the amount of noise that's getting added, this doesn't tell us much. But what we would like is, this tells us, this doesn't tell us, say, if I have a small amount of mutual information and I act on it with a tiny amount of noise, do I keep at least 1% of the amount of information I had at the start? This can't address that question because my question, it concerns the ratio of the correlation measures rather than the difference. Okay, so we say that what we're interested. Okay, so we call this additive stability, or well, it's just continuity really. And what we're interested in this case is multiplicative stability. So that means if I have some mutual information on some state, I want to know, hey, well, one thing I do know is that the mutual information always goes down if I process the B system with some channel. So this inequality will never hold. But I want to say, well, what if I had 0.001? Can't I keep a 0.1% of the amount of mutual information if I'm willing to make the depolarization as small as possible? If I make it non-zero, but something, I shouldn't immediately lose all of the correlation. I should be able to hold on to some of it. That's I should keep at least a tiny fraction. And that's the intuition that I'd like to explore. And we can show it in some cases. So we can show this multiplicative stability for the following cases. One, classical channels and classical noise process, or classical states and classical noise processes. So classical systems. Two, if I'm looking at specific states row, for example, for which correlation measures, this is for mutual information and for relative entropy. Okay, so if I start with a given relative entropy between two classical states, and I run this, I take a tiny little step, I add a tiny amount of noise, it can't make this go down by an absurd amount. It can only make it go down by like at least some fraction of the initial difference between the two states, or the initial relative entropy is still there. I can show this also for relative entropy. Did I call it D over here? Okay. We'll call it D. We can show this also for specific states. If I have one of the states I'm comparing to the other, if I fix rho and then I let sigma be equal to the projector of the semigroup that generates the noise process. So the projector onto the fixed point space of the semigroup that describes the noise process. If the two states are related in this way, if I just project rho down onto the fixed point space, then also I will have a multiplicative stability for relative entropy. And if the states both commute, and they commute with their fixed point destination, then they will also be able to, we'll also be able to show multiplicative stability of relative entropy. And the method here, I'm not going to talk about. Basically, you can express these as an integral of a bunch of norms, and the norms are much easier to deal with than the things with logs of matrices, and it works well. However, it's not true in general. So I want to give you a specific state and a state where we see where we don't have multiplicative stability. So in particular, we have an initial amount of mutual information between A and B, and no matter how small the noise, the amount of depolarizing we add to it, after that amount of depolarization, the mutual information, like 100% of it's gone. It's a vanishing fraction of the mutual information remaining. And I can define it in terms of a state phi theta. It's just cos theta phi theta, or cos theta 0 plus sine theta 1. So if I take the circle through the equator of the block sphere, it looks like this. And I define some state rho theta at time 0 is going to be equal to the mixture of phi theta and phi minus theta. So either I have this state or I have its mirror image, and A just knows which I have. You can calculate what the mutual information is for this state. And then what you can, the next thing that you do is you can depolarize this a little bit. And you can say, what's the mutual information in both cases, both before and after I depolarize? You can calculate those, and you can get, for any fixed amount of depolarization, you can get a ratio of the mutual informations of initial, final, initial, that is smaller than any constant. It's 1 over log 1 over the theta. So you pick the amount of depolarizing you're going to do. I can pick a state that has mutual information that's going to get 100% obliterated by that depolarization. So some states at least have very, very delicate correlations in the sense that while you have this continuity of the mutual information, it can drop down very fast as soon as you start adding noise. I promised to tell you some applications, but I'm coming to the end of my time, so I can just tell you in words what those applications are. One, we find sort of a toy example of a quantum channel that has very interesting property that it almost always gives the input directly to the environment. However, it nevertheless has some positive private capacity. You can send private messages to the output in a way that they're totally obscured from the environment. I can just, and the other thing I could say is we can use the multiplicative stability of coherent information and of quantum advantage to find new examples of quantum channels whose quantum capacities we can evaluate. And that's an outstanding problem. In information theory, typically we're not able to evaluate quantum channel capacities. And this multiplicative stability is a tool that can allow us, when we can prove it, to show additivity in new situations. And with that, I believe I am out of time. Is that correct? Oh, summary. I should, okay. All right, I left out the jokes. Okay, I got to tell you the joke, okay? So this question, how much does noise cause, how much does a little bit of noise degrade the correlation between two systems? I was reminded of it when I saw John's talk, and he mentioned this Bill Unruh paper, right, about how decoherence is going to screw up quantum computers. It's kind of the same notion, same intuition that, well, if you have a little noise, it is going to cause, his intuition was that a little noise is going to cause a big problem for you in a quantum computer. And I used to work at IBM, and there was an old story about this talk where Bill Unruh gave the talk, and he said, well, I hate to rain on your parade, but I think this noise is going to be a bigger problem than you're expecting. Rolf Landau's in the audience. And he says in this loud, deep voice, it's going to take more than rain to stop this parade. And that was a phrase that we repeated many times in my days at IBM when we were in a situation where we felt the evidence isn't being taken into appropriate account. People are marching forward regardless. So it's going to take more than rain to stop this parade is something that I think a lot of these days. And anyway, that was my joke. So that uses up my time, and now I'll answer questions.